This video talks about graphing a proper rational function, and the reason why it's called proper is because my power here is a 1 in the numerator and a 2 in the denominator, and whenever the power of the top is less than the power of the bottom, we're going to go ahead and call it a proper rational function. And it has some unique features to it versus other types of rational functions, and mainly the main one is that its horizontal asymptote will be along the x-axis, or it will actually be the x-axis, or y equals 0. But we're going to walk through everything here. Now, if you're wanting to learn specifically about asymptotes, that's on an earlier video that you could find on Canvas. But I'm going to go ahead, and I already did all the work for the sake of maybe keeping the video at a reasonable amount of time, but I'm going to take you back through what I did and what it means to the graph. So the first thing is finding the y-intercept, and of course we always find y-intercepts by letting x be 0. And when I put 0 in here and here, I'll just get -3 over -4, or 3/4, and we have our first point. It is right here, 3/4 of the way up on the y-axis. Okay, then we factor, and the best we could do on the top is factor out a GCF of 3, and on the bottom it factored into the difference of two squares, because it was originally x squared minus 4, and now I have x minus 2 times x plus 2. That's the factorization of that. Okay, so now what we're going to do is we're going to go ahead and use the factored form to find some specific things. Number one, the domain. The domain is going to be limited in that you're not allowed to ever divide by 0. And since these are rational functions, it does give that potential where we would end up putting an x value in here that would cause me to have 0 in the denominator. And the way you find those values is you just set the factored denominator equal to 0, use the zero product property, which says here that if x minus 2 was the 0 factor, giving me a product of 0, then x itself must have been 2. And if x plus 2 was the factor that produced 0, then x could have been -2. Well, not only are they values then not allowed in the domain, in other words, the set of all x for the domain would be only x values that are not 2 or not -2. They're also the places where I'll have vertical asymptotes, right? Meaning that I'm not allowed to be at those values, but as I get close to them, I end up with extreme behavior where, for example, when I put 1.99 in something very close to 2, I get a really big negative value. And when I put 2.01 in, I get a really big positive value. And so I'm going to see some extreme solutions as I get really close to those asymptotes. But let me go ahead and I'm going to grab a ruler. And I want to put those asymptotes in, and so they are at -2 and +2. And on the video about asymptotes, I talk more about why we end up with that extreme. But real quickly, I could tell you that when you put values in, and I found these values from the table feature, I could show you here. I'll just show you one, for example. But like where I am approaching 2 from this left side, so like 1.99, what happens is if I turn this on, I already have my function in there. You can see it right there. And if I use the table feature and hit second table and put in something like 1.99, that is where I'm getting -74.44. So what's happening is my behavior along approaching 2 from the left, it's going down and getting extremely big negative values as an output, right? And so let me just fill this in with the other values that I found as I got close to these asymptotes. At 2.01, I got 75.56, and so 2.01 was approaching this asymptote from the right-hand side, and that means the values are getting extremely big, positive. And then when I approach this asymptote, -2, From the right-hand side, negative 1.99, I got a really big positive value, so this is going up on this side of the asymptote. And at negative 2.01, which is approaching from the left, it's going extremely down on the negative side of things, right? And so I have some idea of what my graph or function is going to look like as I get close to these asymptotes. Let me go ahead also, let me see, I think I'm going to go ahead and talk about getting the horizontal asymptotes and the x-intercept. And for that, we're going to go ahead and take a look at the numerator, right? And here's why we end up looking at the numerator. Well, to find the x-intercept, you really just set y to be 0. So if I let f of x be 0, and I set it equal to the factored form of my function, when I cross multiply here, I'll get 0 times this is 0, and is equal to 3 times the quantity x minus 1. And when I bring this 3 over and solve, I'll get x is equal to 1. I have a point. It's my x-intercept at 1, 0. And so the factors of the numerator really are where I'm going to go ahead and find, I see x minus 1 equals 0, x would equal 1. The reason why the factors of the numerator are going to produce my x-intercepts is because when I do the cross multiplication, the denominator gets multiplied by 0 and goes away. So I'm going to end up right here at 1. Okay, and there's my x-intercept. There's my y-intercept from earlier. And now what? Well, now we better take a look and see about a horizontal asymptote. Well, the way you could find a horizontal asymptote is through division. We're going to see eventually there's a pattern, and it turns out that anytime you have a proper rational function, which we said at the beginning we do, power of 1 and a power of 2, smaller on the top than bottom, we'll always have a horizontal asymptote at y equals 0, the x-axis. But I could prove that to you here with some long division as well. That if I went and divided the original denominator into the numerator, I'll still have the exact function. It's just in kind of like a mixed number form, almost like when you would take something like 7/3, and if you divide 3 into 7, you get 2 1/3. That is still a full 7/3, but it's in a mixed number form. So when we divide x squared minus 4 into 3x minus 3, you can't multiply x squared by anything and get an x term. It's too big. So that's 0 times that. And when I subtract that, I get 3. When I take 0 away from 3x minus 3, I still get 3x minus 3, which is now the numerator to a fractional remainder of 3x minus 3 over the divisor of x squared minus 4. So really, for really big values, and this is what's helpful in this kind of mixed number form, is to think about what is the behavior of this function like for really big values out to the right or really big values out to the left. Well, as the x values get big enough, the numerator is not growing as fast as the denominator because I'm squaring x here, and here I'm only multiplying x by 3. So eventually, for big values, the function starts to behave just like f of x equals 0 or y equals 0. And that is why this is going to go ahead and be our asymptote, our horizontal asymptote. So it's a little hard because it's the x-axis already drawn there to give you an imaginary line down there. Maybe I'll extend it out here so you could see it. But all along that x-axis is where our graph is going to approach as we go out to infinity and negative infinity. I did notice, though, if we have an x-intercept at 1, we must be crossing somehow. It looks like we're going to cross that line, right? But eventually, out here for big values, we're going to go ahead and approach that line, that horizontal line, right? Okay, so let's just go ahead and prove. Now, I showed you that what I anticipate happening with our function, but let's just throw some values in there, much like we did in looking at the behavior near the vertical asymptotes. So when you put big values in here for x, like 100, and again, I'm just using my table feature, and if I put 100 in there, you'll see how I got that value that I already have recorded right here, right? When I put 100 in, I got a very small value. it's just barely above 0. It's a positive value, meaning that it looks like out here I am just a little above 0, right? So my graph is coming down like that somehow. I'm anticipating this, somehow coming down like this, right? Okay, now, did it ever cross somewhere? Well, we know it crossed there, okay? But a proof of whether a horizontal asymptote gets crossed any particular point other than that particular x-intercept there is through setting the function equal to the horizontal asymptote and solving that equation. Well, think about it right here. What I really have is the same solution that I had up here. It turns out that when I go ahead and cross multiply here, I'll get 3x minus 3, and this is 0. And the only solution was at 1. And so that was the only place I'll ever cross. And the reason why I find out where I crossed the horizontal asymptote is that I am saying, is there a solution where the function solution and the horizontal asymptote's solutions are the same, and it's only at 1 where that is true. So at 1, 0, we have a solution to the function and to the horizontal asymptote, the only crossing point. So with confidence then, I could follow the behavior near the vertical asymptotes up, down, and also use these points and have a sense that my line is going to go like this. And then also, I already filled this in, right? We had that sense. And if you look over here on this side, I'm thinking that if this is my horizontal asymptote that I'm approaching, and take a look at negative 100, I was just slightly less than 0. I think this is coming up here like this, and then curving and approaching the x-axis from underneath. I'll never get to 0, right? We know that the only place where I actually had 0 for a y-coordinate on my function was at 1, 0. But I am running underneath, and this negative 100 helped me feel confident that I was doing the right thing, because when I put negative 100 in, I got a very small but negative value, meaning as I get out here to negative 100, I'm getting ever so close to the x-axis, but I'm not reaching it.